Hello folks, um, this is the series of videos related to the sequences. So this is the first part, and I'm gonna go over some examples related to the sequences today. And here I have a couple examples about the sequences. Of course, like mainly when I talk about the sequences, I'm talking about their limits. So I'm not just really write down any kind of definitions, but I'm going to go over some examples and I'll mention about the definition. So the first example is just really a basic one. What can we say about the limit as n goes to infinity of a geometric sequence, like something like 2 to the n? So we're really trying to find the limit as n goes to infinity of 2 to the n. You may list some terms. I mean, this is just powers of 2. So n starts by 1. So 2 to the 1 is just 2. Squared is just 4. Cubed 8. 16. And so on. So as you see, these numbers are really getting larger and larger. We don't have a bound for them. So they really goes to infinity. And we just say this sequence just diverges to infinity, and we just say the sequence is just either divergent, or we say it diverges to infinity. Both of them really works. So this really this is a really good example related to a sequence which diverges to infinity. And here is another example of a geometric sequence which is actually convergent. So what can we say about the limit as n goes to infinity of 2 over 5 to the power n? So you can really see this time we have 2 over 5, the powers of 2 over 5. So if you list it, it will be 2 over 5. The next we're going to get 4 over 25. The next we're going to get 8 over 125. Then this will be 16 over 625. As you see, the ratio 2 over 5 is kind of like 0.4. This will be 0.16. You can multiply by 4 and you can just see 16 over 100, which is 0.16. So this is like 0.4, this is 0.16, and you can calculate the others, but it's just getting smaller and smaller. As you see, the denominator will get larger much more faster than the top because 5 is greater than 2. So this sequence will just go to 0. So the limit is just 0, and we call such sequences, if the sequence goes to a number, approaches to a number, then we call it to be convergent. Or in the similar way, we can just say it converges to 0. So these are just the first two examples that we covered. Now the next and the last example is just about limits at infinity. I'm just going to show you a straightforward technique that you can apply. Limit n goes to infinity, can just say 4n squared plus 1 divided by 7n squared plus 3. So you can see the degree of the top is 2 and the degree of the bottom is 2. So if you want, I can just write as method 1. I can just say method 1. This is the classical way that you just divide everything by n squared. So you have 4n squared plus 1 over n squared, and then you have 7n squared plus 3 over n squared. So that way you can just write them separately, and that will be limit n goes to infinity. We have 4 plus 1 over n squared here, and then we have 7 plus 3 over n squared. So as you can see, 1 over n squared, and here 3 over n squared approaches to 0 as n goes to infinity. So basically you just add them, 4 plus 0, 7 plus 0, so that's just 4 and 7, so it's just 4 over 7, and we just say that the limit is just 4 over 7, and this is convergent. Here's another way that's really a straightforward, nice way. This is method 2 that I really want to mention. This is, you all know about it, it's just L'Hopital's rule. We solve this problem. So L'Hopital's rule, I mean, you know, it's just, it can be applied to any limit of type infinity over infinity, or it should be 0 over 0 type. And here, of course, we have sequences. However, by a famous theorem, you can really evaluate the limit of the function as x goes to infinity. You can just say 4x squared plus 1 over 7x squared plus 1. You can evaluate this one, and you can see this is of type infinity over infinity. Why? Because limit of a polynomial px as x goes to infinity is negative infinity or positive infinity, depending on the leading coefficient. So here, leading coefficients are positive, 4 and 7, so they are both infinity. And you just take the derivative of top and the bottom. So the top will be simply 8x, bottom will be 14x, and you can see x's will cancel, and we will simply get 8 over 14, I mean, which is 4 over 7. So we get the same answer. So this is another cool way to apply a problem of this type. If you have two polynomials at the bottom and the top, or just like radicals of two polynomials, I'm going to show this in part 2. You can really apply this method. It's just like one straightforward method, and just applies the L'Hopital's rule. Okay. Hope this video will be helpful, and thanks for watching, and see you next time. Bye.